Welcome to Massive Open Online course on basic principles and calculations in chemical engineering. So, we are discussing about energy balances on reactive processes and also non-reactive processes in our earlier lectures, and under the module 7 we have discussed about this with ample of examples. Now, in this lecture we will try to give more examples regarding that energy balance on heat of solution, and we have covered that energy balance with multiple streams without reaction, energy balance also with the different streams in the specific chemical engineering operation like evaporator, dryer, distillation column, and also refrigeration processes. Now, here also we have to find out that how actually that enthalpy balance can be helpful to analyze the solution basically for acid or other different type of solution. Though we have discussed different aspects of that mixers and also how to calculate the enthalpy changes of mixers in a particular process there, and based on that mixer specific heat capacity as also that temperature change, how those energy can be calculated based on that internal energy change and also kinetic energy change inside the system. So, that solution also can be considered as a mixer where that enthalpy change can be calculated based on that input and output streams, and as well as that the different components enthalpy change based on their formation, and also how that sensitive heat is changing during its phase change. So, we will extend this enthalpy balance or energy balance equation for analysis some other problems here with solution. So, before going to that we have to look back that energy balance equation, like we have actually described that energy balance equation in the form of internal energy change, kinetic energy change, potential energy change, and also flow work change based on that pressure change and volumetric flow rate change. And those that energy as a sum that will be contributed by the net energy supply to the system. Now, that net energy supply to the system basically comes from that heat energy supply to the system and how much work is done by the system there. So, that balancing of that energy would be contributed to that internal energy, kinetic energy change, and potential energy change. Even if there is a pressure between these two streams of inlet and outlet, if is there for the process, then you have to consider that flow work change there for the energy balance. And based on that continuous operation and also the continuous supply of mass, then how that internal energy, kinetic energy, and also potential energy will be changed because of that flow work and heat energy supply to the system. And that overall energy balance can be expressed based on that specific energy terms, but just by multiplying that the mass flow rate as a common factor in the common energy balance equation. That also we have described earlier. So, here in this slides also it is given that this how that energy balance equation can be written based on that specific energy terms with that mass flow rate. And finally, if you are considering that there is no shaft work, there is no kinetic energy change, there is no potential energy change, then you can simplify that energy balance equation as like this here, q dot will be equal to delta H dot here, and based on this enthalpy change, you will be able to assess that what will be the heat energy required to change that operation, or what will be the energy required for the actually that execute that process there in the system. So, let us do an example with a solution where that heat can be removed or maybe added to keep that final solution at a certain temperature. Now, in this case, suppose in a closed constant pressure system of flask that you are about to dilute suppose 2 mole of 100% sulfuric acid with enough water to produce a 30 mole percent aqueous solution. In this case, the acid and water are initially at a temperature of 25 degrees Celsius to be considered. Now, in this case, here see that there is a sulfuric acid solution of its 2 mole capacity, and which is mixed with that enough water to produce that 30 mole percent of aqueous sulfuric acid solution there. So, in this case, how much heat would be actually removed to keep that final solution at that 25 degrees Celsius, because there that some heat energy to be removed to get this dilute solution of the sulfuric acid. In this case, that heat of solution is required and it is given that it will be amount of minus 44.28 kilojoule per mole of sulfuric acid at this condition. Another condition that if you supply that a mass of 150 gram of that flask with the solution, and the heat capacity of the flask is known to you, and it contains its contents is 3.30 joule per gram degree Celsius, and if the flask is sufficiently insulated so that it will be the system will be as a that adiabatic system, and in that particular condition you have to find out what will be the final solution temperature. So, this is the problem based on which you have to assess it by energy balance by equation. Now, to solve this problem, first of all you have to calculate what will be the amount of actually water to be mixed with that 2 mole of sulfuric acid to become it as a diluted 30% sulfuric acid solution. So, for that 2 moles of sulfuric acid to make it you have to add some water that is not known to you. So, for that if you consider that n mole of water is required for that, then we can write that material balance for this solution as for this 2 mole of sulfuric acid, that will come from that whatever solution to be made of that will be 30%. So, 30% of that sulfuric acid out of that total amount of solution will be equal to here 2 moles of sulfuric acid plus n moles of water. So, this is your total moles. So, total moles, out of this total moles, that 30% of this moles will be sulfuric acid, that will be equals to 2 mole of sulfuric acid. So, if you write this equation of that mole balance of the sulfuric acid, you can calculate what should be the moles of water to be required for getting that 30% sulfuric acid solution at its diluted condition of 25 degrees Celsius. And then if you are getting this amount of water, that is as per calculation it is coming as 4.67 mole of water. In this case, then what is the ratio of this sulfuric acid mole to the water mole, and based on which you can assess what will be the amount of heat of solution to be required to get this diluted solution at this 25 degree Celsius. So, for that what will be the ratio of that water moles to that sulfuric acid, that is basically that 4.67 divided by 2 here. 4.67 is the mole of water and 2 is mole of sulfuric acid. So, it is coming as 2.33. So, at this ratio of the sulfuric acid and also that water, here you will see that at its 2.33 value, that heat of solution at 25 degrees Celsius is around minus 44.28 kilojoule per mole of sulfuric acid. So, in that case what would be the total heat is actually to be removed from that system of this diluted sulfuric acid there. So, as per that energy balance equation, we can write that here simply that there will be no shaft work, there is no kinetic energy change here, there is no potential energy change here. So, finally, we can write that this energy balance will be equal to Q, that will be equals to delta H, that is enthalpy change there. So, for that enthalpy change for that solution at its ratio of 2.33, it is coming here delta H S hat, that is per mole of sulfuric acid, what will be enthalpy change. Now, since there is 2 mole of sulfuric acid, then total enthalpy change will be equal to N of sulfuric acid into specific heat of solution at this 25 degrees Celsius and the ratio of water to the sulfuric acid mole. So, according to this finally after calculation you can get this minus 88.6 kilojoule of heat is to be removed from the solution. Now, this mass heat is actually produced during that addition of that sulfuric acid in water there. That is for making that solution, you will see there will be a heat generation and that heat should be removed by that removed to the atmosphere, so that certain dilution at a certain temperature it would be reached there. So, you have to then calculate what will be the final temperature of that solution there if you are removing this amount of heat from that solution. So, for that you have to calculate what will be the mass of solution of that 30% sulfuric acid solution. So, in this case you have to then add up of that what will be the mass of sulfuric acid and also what will be the mass of water in a solution. So, mass of sulfuric acid can be calculated just by multiplying this 2 mole of sulfuric acid by a molecular weight of sulfuric acid. So, it is coming as 2 mole of sulfuric acid into 98.08 gram of sulfuric acid per mole. And then what will be the mass of water, that can be calculated again just by multiplying that mole of water by its that molecular weight. So, it is coming as here 4.67 mole of water multiplying by 18.0 gram of water which is molecular weight of water. So, finally, after adding this you can get this 280.2 gram of total solution. Since here again doing that enthalpy balance there in a solution, it is true that in a net that enthalpy change will be equal to 0. So, finally, we can say that at this 25 degrees Celsius we can say that enthalpy change will be equal to 0. So, what is the enthalpy basically that is actually what will be the amount of sulfuric acid and what will be the heat of solution at that 25 degrees Celsius of the diluted solution, plus there will be a certain change of that temperature, that is sensitive heat to be changed because of that change of temperature there. So, that temperature you do not know, you have to find out. So, let us consider that temperature as T, which is to be found out. So, here if we multiply this mass of that solution and also that specific heat capacity of the solution at constant pressure and the temperature difference, then you can get this sensible heat change there. So, what will be the heat of solution and what will be the sensible heat change there, that you have to add it up to get that total enthalpy change will be equals to 0. So, we can write this equation here shown in the slides to balance that heat at its diluted solution of that amount here to 280.2 gram. So, after substitution of this value of here enthalpy, this is simply what is that this value is already calculated here in part A. So, this is minus 88.6 kilojoule, and this part here M is calculated as 280.2 and plus here 150 gram there total amount of this solution as well as their extra water is supplied for the dilution. For that you have to add it up. So, this is your total mass of that, and then what will be the specific heat capacity that you have to multiply. This is basically 3.3 joule for the solution, and a temperature is change is T minus 25, because the initial temperature was 25 degrees Celsius, and when final temperature is that T. So, T minus 25 degrees Celsius, this will give you that temperature change based on which that what would be the sensible heat change there. So, finally, you can get after calculation that T will be equal to your 87 degrees Celsius. So, you can say that if you add some water there, you will see that solution temperature will be changed there. So, accordingly you can say that that how temperature will be changing because of the dilution or concentrating that solution also. Accordingly you can calculate here as per this enthalpy balance equation. Now, let us do another example for assessing that energy balance equation with this example here. Let us consider that water is added to pure sulfuric acid in a well insulated flask initially at 25 degrees Celsius and 1 atmosphere to produce a 4 molar sulfuric acid solution where specific gravity is given to you. The final temperature of the product solution is to be 25 degrees Celsius. So, that the water added must be sealed liquid at temperature less than 25 degrees Celsius or a mixture of liquid water and ice. Now, in this case you have to consider a basis of calculation 1 liter of the product solution, and assume Q will be equal to delta H, that is heat energy supplied, that will be equal to enthalpy change for the process. Now, if you need to know the heat capacity of ice, and you can take it to be half that of a liquid water. Now, in this case if only water is added, what masses of sulfuric acid and water should be mixed, and what should be the initial temperature of the water, that you have to find out. And also if a mixture of liquid water and ice is added, then how many grams of each should be fed to the process. Now, to solve this problem, basically you have to consider that basis of that problem. Here basis is 1 liter of 4 molar sulfuric acid solution is considered, and specific gravity of that solution is 1.231, it is given to you. So, 1 liter means here 1231 gram you have to multiply to this 1 liter, so that you can get total 1231 gram, because the specific gravity is 1.231. So, what should be the density of that solution? It will be simply 1231 gram per liter. So, here in this way you can calculate the mass of that solution is 1231 gram. Now, in this mass there will be 4 moles of sulfuric acid, that means here 1231 minus 392.3 that will be your total amount of water. Here 392.3, this is basically that 4 moles of sulfuric acid, how much it will give you that weight. So, in that case if you subtract this amount of sulfuric acid from the total solution, then you can get this what will be the amount of water there. And you can say that this water moles will be is equal to 46.57 mole of water, because if you divide it by molecular weight of water, you can get this moles of water there. So, in this 1 liter of 4 molar sulfuric acid solution contains this gram of sulfuric acid, that is 392.3 gram of sulfuric acid and 46.57 mole of water, or you can say 838.7 gram of water. In this case, what will be the ratio of that water to sulfuric acid? It is simply as per this calculation here, 11.6 mole of water by mole of sulfuric acid here, just by dividing this here 46.57 mole of water divided by 4 moles of sulfuric acid, then you can get it simply 11.64 mole of water per mole of sulfuric acid. This is your ratio. Now, this ratio will give you the heat of solution. So, this heat of solution is coming as minus 67.6 kilojoule per mole of sulfuric acid. So, you can get it from a table what is given in your textbook there in the appendix, that how heat of solution can be changed to the ratio of solid to solvent there. So, in this case as per reference here, it is given that water and sulfuric acid based on which that heat of solution can be calculated. Now, if you consider that in the solution that only water as a liquid substance, then what will be the amount of this water is coming into the system, as it is 46.57 that we have calculated here, this mole. So, what will be the enthalpy in the inlet? That is simply that 0.0754 into T minus 25. T is the temperature that you do not know, that you have to find out there for that solution. Whereas you know that what will be the moles of water in the outlet condition is not known, because here this is a simple batch process. There is no continuously supplying or that is continuously outlet of that mole here, it is considered there. So, here in this case N out and S out to be nil. Similarly, sulfuric acid that will be 4 mole, and also you can say that here enthalpy will be equal to 0. Now, question is that why this 0.0754 it is coming, because this is the mole ratio that you have to consider there. And then what is that here sulfuric acid at this ratio, that N of sulfuric acid nil, and enthalpy change of that sulfuric acid is nil. Whereas in output there will be sulfuric acid out at 4 mole, and here this enthalpy of this outlet stream is minus 67.6. So, finally, if you do that enthalpy balance based on that earlier equation that we have given, then we can have this temperature as minus 52 degrees Celsius as per after simplification of this balance equation by substituting this various variable. Now, at this condition 2, whatever it is given in the problem, that water as a liquid that is coming in, that will be equal to N1, that is not known to you, that you are considering here, it is N1. Whereas in enthalpy at this inlet condition, it is given as this, and in the outlet there will be no water. Similarly, for water solid, in that case what will be the amount of solid is there, it is not known to you, that you have to consider here as unknown. and also enthalpy change for that solid water you can calculate. By this simply you know that this amount what is the heat of formation, and then what will be the enthalpy of that sulfuric acid because of this temperature change. And then sulfuric acid as a liquid that is given to you, that is 4 moles, whereas in that sulfuric acid at 25 degrees Celsius where this ratio as per ratio here it is 11.64. At this ratio that that in total output of this sulfuric acid is 4 moles, and enthalpy change at the outlet condition it will be equal to minus 67.61. So, again you know that from the table of that solution enthalpy of solution you can get this specific heat of solution for that amount of solution that you can calculate from that table which is coming as 6.01 kilojoule per mole. Then total amount of liquid and solid that will be coming as as a material balance. You can have this balance equation for this liquid and solid in inlet and outlet condition. So, finally, you can get this N1 plus NL plus NS that will be equal to 46.57. So, as per enthalpy balance, that heat of solution will be equals to 0 there. So, accordingly that enthalpy change, if you calculate it from the inlet and outlet streams, then finally you can get after solving this equation as N1 will be equal to G for 16.18 mole of liquid of water, and NS solid that is ice that will be 30.39 mole of ice. So, based on this equation you can also solve this whenever the solution will be cool down to a certain temperature by a by supplying some sink heat sink like ice like that. So, what will be the amount of ice to be supplied, and also what will be the water to be mixed with that acid solution to get its final temperature of T temperature, like this here in this case this final temperature is considered as 25 degrees Celsius. So, accordingly what will be the amount of heat is required that you can calculate, and also from that heat balance and material balance you can calculate what will be the amount of liquid and also ice required for the making of solution. And another example let us do here. In this case an 8 molar hydrochloric acid solution. The specific gravity of the solution is 1.12 and specific heat capacity at constant pressure is given 2.76 joule per gram degree Celsius, is to be produced by absorbing hydrogen chloride as a gas in the water, and liquid water enters the absorber at 25 degrees Celsius, and gaseous hydrochloric acid is fed at 20 degrees Celsius and a pressure of 790 torr. That is 1 torr means 1 millimeter mercury pressure. This is absolute pressure, and in this case you have to remember that that all of the hydrochloric acid fed to the column is absorbed in the liquid system, and then take 1 liter of product solution as a basis of calculation here. So, based on this problem you have to estimate the volume of hydrochloric acid that must be fed to the absorber, and also you have to calculate the heat that must be transferred from the absorber if the product solution to emerge at 40 degrees Celsius, and also you have to estimate the final solution temperature if the absorber operates adiabatically. So, to solve this again you have to take that basis of 1 liter product solution, and whose specific gravity is given and also that specific heat capacity is given. So, as per that you can get this 1120 gram solution of that hydrochloric acid. Now, based on this you can calculate what will be the gram of hydrochloric acid there, since here 8 mole of hydrochloric acid. So, if you multiply it by its molecular weight, then you can get what is the mass of hydrochloric acid. So, remaining amount will be that water that can be calculated here. It is as per this problem, it is 8 to 8 gram of water. So, in this case what will be the mole of water, just dividing it by its molecular weight, then you can get this mole of water. And what will be the then ratio of that water to hydrochloric acid solution? It is coming as 5.75, this is as here N, or sometimes it is represented by R as ratio. Now, assume all hydrochloric acid is to be absorbed in the absorber. So, in this case volume of gas that will be equal to 8 mole of this hydrochloric acid hydrogen chloride gas to be absorbed. So, in this case 8 mole of hydrogen chloride at this temperature of 293 K as per problem, and also the pressure of 790 millimeter mercury. Accordingly, what will be the volume of that, because per mole of gas will give you that 22.4 liter at STP condition. So, as per that and also from the equation of state of gas, you can calculate that this 185 liter of gas feed per liter of hydrochloric acid solution, which is to be absorbed in the absorber here as shown in the slide. So, we can then calculate this amount of gas to be absorbed by this absorber there. Now, if we consider that reference temperature, what should be the enthalpy for that individual components in this absorber? What are the inlet and outlet? Of course, as per this schematic diagram, this is the amount of hydrochloric acid, this is which is going to that absorber, and this is here aqueous hydrochloric acid solution. So, finally, you will see that this amount of hydrochloric acid aqueous solution of hydrochloric acid to be made if you absorb this hydrochloric gas at 20 degree Celsius of 790 millimeter mercury there, and from this initial solution of 46.0 mole of water there. So, accordingly, what happened here, this mole of water will be absorbing some hydrochloric acid gas, and finally, you will see that 1 liter of hydrochloric acid to be made. Now, in this case, what will be the inlet, what will be the outlet? Very interesting that this amount of hydrochloric gas or hydrogen chloride gas, it will be in, and this amount of water to be in, and this is your outlet condition. So, here 2 inlet and 1 outlet is there. So, accordingly, that inlet, you will see that water inlet is 46 moles and enthalpy is 0, whereas hydrogen chloride gas inlet at 8 moles and also enthalpy change is minus 0.15. And in the solution, you will see that heat of solution at this ratio, that we can say that inlet condition there will be no hydrochloric acid solution at the inlet condition at this ratio. So, that enthalpy and moles will be 0, whereas it will come from this outlet, whereas moles of that hydrochloric acid will be N out will be 8 moles, and this enthalpy change will be minus 59.07. Now, according to that, what will be the enthalpy, specific enthalpy of this solution at this 25 degree Celsius, and how then sensible heat will be changing out of this hydrochloric acid from the temperature from 25 to 40 degree Celsius. So, if you substitute those values here, then finally you can get this value of 0.15 kilojoule per mole of this hydrochloric acid at 20 degree Celsius. And then that according to that enthalpy balance, or you can say that heat energy balance, so we can get this total enthalpy change will be equal to, if you multiply this minus 15 point kilojoule and the total mole of that hydrochloric acid solution there, then accordingly you can calculate here. This will be your amount of kilojoule or heat energy that is to be removed per liter of that hydrochloric acid solution. So, in this way you can calculate the enthalpy balance, or you can do the enthalpy balance equation to calculate that what will be the amount of heat that is to be removed for its dilution or by absorption of even some gases by other liquid also. And from this heat balance or energy balance equation, you can say that at what temperature that solution will be reached there. So, since the final solution will have that enthalpy change will be equals to 0. So, accordingly if you consider that temperature is T, then if you substitute that respective term here in this balance equation, you can get the final temperature of 192 degree Celsius. So, we can solve this status of solution based on this energy balance equation for the assessment of what will be the amount of heat should be added or heat should be removed for making a certain extent of dilution of that solution. So, I think these problems will be helpful for you for further solving the problems related to this problem there. And for this you have to sometimes use the data that is given in tabulated form in appendix of this textbook. You have to consult that data, otherwise the data to be given for your assessment in the problem, so that you can solve the problem different problems related to this solution and its heat energy input and output to make this solution at its particular condition of temperature and pressure. So, in the next lecture we will start the new module where we will discuss more about that material balance and energy balance there, but that material balance or energy balance would be basically for the process where unsteady state operation will be there for chemical engineering processes. So, next lecture we will discuss the portion on unsteady state material balance only. So, thank you for your attention to this lecture.